I thank everyone for coming. This is the title of my talk. What you're looking at there are simulated galaxies in a computer. Today I wanted to tell you more about how we do that and why we do it. The first thing is, I thank everyone for their applause, but we are here to celebrate our grads. And if anybody knows Astrophysical, there is nothing that we celebrate more than the soccer World Cup. This is our last one, and we're holding on to it as much as we can. So to all our grads we are celebrating today, you make us proud, and this is for you. Astronomy is a very visual science. So what I thought I would do first is to start with a picture of dark matter. And you're looking at it. And so I thought this would really not do for a very good talk. And that is where galaxies will start helping us. What you're looking at there is the coma cluster, is a set or a large group of galaxies. You will recognize the members because they tend to be redder than the rest. And the coma cluster is a system about 100 megaparsecs from us. It's quite far, but it's still something that we call the nearby universe. And this specific object is very special to us because it was the first one that made us think about dark matter. So in 1930s, Fritz Zwicky, which is a Swiss astronomer, noted that the galaxies in that coma galaxy cluster were moving too fast. We're moving too fast to be explained by the amount of light that we could see coming from the stars or gas. So then he published his research noting the presence of dunkle materia, or what is translated today to dark matter. Back then, it didn't catch up more. It was just a curiosity that remained in the published journals until several decades later, Vera Rubin, who was studying something completely different. Vera Rubin was studying the motion of stars around galaxies. No galaxies around galaxies, but just stars around the center of a given galaxy. And she also noted that those stars were moving too fast. So stars that were far away from the center were moving at a similar speed that galaxies exactly at the center. And what we knew about gravity was defying that. It should have been going down with distance. So the discoveries of Vera Rubin was the first confirmation or compelling evidence that there was something out there that we were not understanding, new physics, something of the universe that needed explaining. And so this is a rotation curve. This is an illustration of the Vera Rubin sort of research. What you can see, let me see if I can do this. Yeah. So you see, this is a galaxy that is centered here, and we care about the distance from the center. And then at each bin, what you would do is to check how fast the star and the gas is moving. And that gives you this curve that you see here with the symbols in yellow, traced by stars. And then in blue is what the gas gives you, allows you to extend it much more. And you can see exactly here the evidence or the suggestion of that matter. As you move away from the center, the things move faster and faster. Whereas if you were to check what is the real mass that is there in the stars and gas, you would see something like declining like this. This is what Newtonian gravity would give you. So this jump over here is what we call dark matter. Of course, once scientists are presented with something that has no explanation, we get creative. And there were a lot of hypotheses of what dark matter could be. For gas between stars, it could be planets, dark planets, dense planets that we couldn't see because planets don't have their own light. So those objects were called massive compact halo objects. Machos, I don't think they would be called like that today, but there was back then. And then, so black holes or changing gravity or a new kind of particle. We have by now ruled out the first two options. Anything that is made up of the stuff that we know about, of the atoms, of the molecules, of the dust, all the things that we are familiar with cannot really explain what we observe. And we are left with these three options. Of course, it could be more, but those are the things that today are being more intensely researched. Black holes are postulated as possible dark matter candidates. They could explain the whole of dark matter, which seems difficult, but is still not ruled out. Or it could be that a fraction of this mass that we still need in the universe is in the form of primordial black holes. What is fantastic about black holes, besides their proof of general relativity, is that they can, in cases where you have binary systems, they have emission of gravitational waves, a discovery worth the Nobel Prize a few years ago. And that allows us, in a way, to make predictions that can be confirmed or ruled out about the presence of these primordial black holes as candidates for dark matter. Our department is lucky to have, for now, only these two professors working on it, John Richardson, which is one of the organizers of the event today, and Barry Barish, Nobel laureate, connected to the discovery of gravitational waves that you're looking at there with the LIGO experiment. The other two promising facts to an answer are either our laws of physics are different of how we understand it. Maybe gravity behaves completely different out there in the galaxies than it does at the center, that is where we have probed so far. Or it could be that indeed there is a particle candidate that we have not detected yet that can explain all the mass that is missing in the universe. That seems to be one of the most successful theories so far, a particle. Now that particle will have to be very special. It cannot emit any light because otherwise we would have detected. So it does not emit or radiate anything in the electromagnetic spectrum, which makes it extremely difficult to detect. But it does interact with normal matter, interact with dust, interact with stars, with gas, and only does it through gravity. So such a model is one of the ones that has built up sort of the skeleton of how we think the universe works, and is being tested daily on its predictions. We have in our department a very strong group working on this area. I'm listing the main ones, but really it's a collaboration of many more. But so we have 3 UCR theorists or particle physicists that are working on developing these models and making the predictions to then be tested. So Yanu, Flip, and Haibo, you cannot see because I have that thing there, but Haibo Yu, who is also in the audience along with his family, and Sean Westervale is one of our more junior faculties that is working on the experimental side of actually detecting these dark matter particles in laboratories. Sean is also working. But dark matter is not the only weird thing that we have in our universe. So what you see over here is our best explanation for what the universe is made of. Most of it, all of the energy and matter of the universe is explained by 70% of something that we don't know what it is, but we call dark energy. And we know what it should do. It should expand the universe. It should make things repel each other. But we're not really talking a lot about dark energy today. It's extremely interesting, but not time. Now, the mass in the universe is about 30% of that energy budget. And most of it is in the form of dark matter. This dark matter, this particle that we don't know really what it is, and that's why we call it dark. Dark matter and dark energy are really nothing alike And so far, we don't know of any connection between them. It's just that astronomers are not really great at naming things. That's why they're called dark. But they really are not related. And the universe that we really have the privilege of seeing and studying, this 5%. It's nothing. Of all of that, most of it is in the form of hydrogen and helium. And only a very tiny, tiny, tiny portion of it is the stars, neutrinos, and the metals that we, with our eyes, are used to see. So you might think about, why are you so proud of this model? It kind of sucks, because we really don't know a lot. Right? And you are fair. It's a very fair question. This is a personal note, but this is one of the things that gives me the encouragement to believe in this model. So this is the cosmic microwave background. It's an all-sky emission, thermal emission that is coming from the universe, very early universe, showing little fluctuations of temperature. So this signal was emitted 300,000 years after the Big Bang. Nothing has formed yet. This is our first picture of the universe after the Big Bang. Every red dot that you see here is a region of the universe that is slightly overdense. It's a higher temperature, but there is a correspondence with density. And every blue point that you see here is a region of the universe that is underdense. These fluctuations are tiny. 1 in 10 to the 5. They are really tiny fluctuations. They are just here enhanced because this is the prediction that is that the universe is mostly uniform with a little bit of fluctuations. And this is what we measure. Now, you could quantify, in a way, this distribution that I was really not going into details because it's boring. But there's what brings us to this plot that shows, as a function of a scale within this map, something that we call power, but it doesn't matter. What I want you to pay attention to is the fact that the green is a prediction from our theoretical model. It has no free parameters. It's just the prediction. And the red points are the measurements. It is really difficult to get, just by coincidence, such a measurement correct. So while our cosmological model has a lot of uncertainties, we have some confidence that it cannot be or behave too differently from what we are working on already. The cosmic microwave background is one of the best probes of the early universe. And this image is from the Planck satellite, which you can see over here. But new missions are coming. You will see it towards the end of the talk. And a lot of that investment is being capitalized here in our department as well, with the hiring of Steve Choi, which is, I believe, one of our most newest faculty members that joined our department. And after I have talked for a bit, you might be wondering, what are the galaxies? I came here to see galaxies. Well, me too. So here they are, a few examples of these beautiful objects. These are collections of gas and stars that the universe gives us. How we can use galaxies to learn about cosmology. So this is an image showing how we think the universe has evolved. There was the Big Bang that is not even shown. Here is the cosmic microwave background emission, 300,000 years after the Big Bang. After that, there are a few processes that there's the dark ages, there is the emergence of the first galaxies over here. Those galaxies and the photons that the galaxies emit ionize the universe, making it transparent. And now it becomes a universe that we can observe. After that happens, the universe evolves for about 13 billion years. 13 billion years until we're here today. And those galaxies that you saw are formed and telling us the history, in a way, of the whole process. How do we fit galaxies within our model of cold dark matter? The idea here is that we start our universe. This is the initial condition of our universe. A picture of the baby universe when everything was quite homogeneous, but there were seeds that were slightly more dense. Because gravity behaves like economy, the richer get richer, the poorer get poorer. So the peaks that were here slightly over dense, they keep growing and growing. And the things that were under dense, they get emptier and emptier. So those peaks that we see here grow to become massive dark matter halos today. Virialized in equilibrium objects that are very extended and very massive. And these galaxies that we see today are sitting at the very center of each of these dark matter halos. And this is not different for the case of our own galaxy, the Milky Way. This is an image taken from, Joshua Tree National Park, quite local. And if you expose it for long enough, you can easily see the bands of stars and dust that is forming the disk of our Milky Way. We can sketch how we imagine the dark matter halo of our own galaxy. So if this is the center of the galaxy, the sun is at 8.5 kiloparsecs. That's about, 10,000 light years, 15,000 light years. Doesn't matter, just remember 8.5. That's about half the size of the disk of the Milky Way. If you take the gaseous disk, it's a spiral galaxy, so the disk will be about 20 of those kiloparsec units. What we expect of the dark matter halo is that it goes for about 10 times bigger outwards, much more extended than the disk, and way more massive. These are the numbers, more or less, as we think. For our disk is about 6 times 10 to the 10 solar masses, or the equivalent of sun masses. And for the dark matter halo, it's about 10 to the 12. So it's 100 times more massive than the amount of mass that we see in stars and gas. We can measure the rotation curve, like Vera Rubin did for the Milky Way. It is difficult because we're within it. So a lot of the measurements in the Milky Way needs to be special and different from other galaxies because we are embedded in it. But once you figure out the systematics, you can come up with a plot showing the distance from the center of the galaxy versus how fast things are rotating. And you see again this behavior. The velocity does not change with radius, which was used as an evidence for dark matter in other galaxies. It's also true in our own galaxy. If you look at the scales, the sun about 8.5 kiloparsecs, so we are about here, rotating between close to 250 kilometers per second. Now, this is a simpler version of it, but this is still the rotation curve of the Milky Way, and you can attempt to decompose that on the contribution from things in the disk, and whatever is not filled up by that, you attribute to the dark matter halo shown in here. So the location of the sun, where we are, it looks like the disk contributes most of it. So even though the viruses contribute a lot of the mass at this position of the sun, there is still a lot of dark matter around it. It's a lot of dark matter in this move, and the way to think about it is you will find, or the prediction is to find about 1 dark matter particle in the volume of a coffee mug. However, there is a lot more of the other mass. And that's what makes people like Sean Westerdale, that is trying to detect this elusive dark matter particle, work so hard to get there. We said dark matter doesn't really emit anything in the electromagnetic spectrum, so we cannot really see it. So you might wonder how we can really study it. If we really, there's no things that we can measure from it. A way around it is always to make predictions and see if it fits the way in which the matter, the normal matter that we can observe, behaves. And those predictions, because of how complex the evolution of the universe is, cannot be made pen and paper. For that, you need computer simulations. Those computer simulations, we put our best understanding of how the physical law behaves. And then you write it up and you send it into supercomputers. Your computers are not good enough. You need calculations. Imagine we are trying to reproduce what the universe took 13 billion years into a month or a few months, so hopefully your grad students can graduate one day. So that takes a lot of computing, and for that we need supercomputers. We use some of them here in campus, and for the really big scales, we use NSF or European supercomputers. This is the team of simulators in our department, and we all work on different aspects of cosmology, structure formation, and galaxy formation. What these simulations allow you is to actually see dark matter. And this is what I will show you. This movie is showing you the dark matter in a galaxy like the Milky Way. It's only showing you the dark matter. Whatever you see here, you couldn't see in the real universe, but we see it through the power of our computers. You have the time since the Big Bang here. You want to get to 13.7. It starts very homogeneous, and as time goes by, gravity is doing its thing. The structures collapse into a network of filaments that are starting to form the first dark matter halos. You see, the rendering shows density of dark matter. So yellow means places with a lot of dark matter, and purple is lower density, and black means very, very low density. So this whole material will flow into the center and finish within the halo of the Milky Way. So the Milky Way in the early universe occupied a very extended space. One of the predictions of whole dark matter is this granularity. You see that most of the mass, or a lot of the mass, is concentrated on individual, what we call halos, clumps of dark matter that are growing with time, and at the same time they are coming together and aggregating into something that is the proto-Milky Way. This is about a third of the age of the universe, not yet, but the seed of the Milky Way data is already there. And you see a lot of activity, a lot of aggregating of these clumps on a process that we call mergers. These are, remember, each clump should host a dark matter. Each clump should host a galaxy. So these galaxies will be coming and interacting and merging with each other. By this time, about half of the mass of the Milky Way is already in equilibrium. So the Milky Way has half its total mass, and it becomes much more quiet. The accretion history is less chaotic, and it starts to just aggregate more and more of this substructure that is orbiting in its gravitational potential. Do we have any evidence that this is correct? We have some. We know that the Milky Way, as well as Andromeda, is surrounded by several small galaxies. Over here, you have what we call the local group of galaxies, Andromeda, the Milky Way, and each point that unfortunately you cannot read the names, me neither, but that's because my eyes are bad. Each point is a small galaxy. It's a galaxy, a low mass galaxy. It's still a conglomeration of stars, gas, and dark matter. But 100 to 1,000 to 10,000 lower mass than our own Milky Way. And there are many of those around any galaxy in the universe, or at least that is the prediction. There should be these companions. For each big galaxy, there should be a handful, many hundred thousands of low mass or dwarf galaxies. Over here you have a few pictures showing some of the famous dwarf galaxies in our own Milky Way. These galaxies, this is Draco, Fornax, Sculptor. Those are some of the most, we call them classical satellites because they were discovered a long time ago. They are orbiting in the gravitational potential of our own halo. And there is this new kind of galaxy that we call ultra-faint because you can't really see it. These are resolved individually by star by star. They are so faint that you cannot really see them in a picture. Those are being discovered monthly. So the census of galaxies, of dwarf galaxies around the Milky Way is changing all the time. We always keep our tables as updated as we can, but we always have to, keep adding new entries. And this is fantastic because this is the prediction of cold dark matter. Many companions, a lot of granularity in the universe. You can now check how fast these things are moving, and this is a picture of the large and the small Magellanic Cloud. Those are the two most massive satellites in the Milky Way. They are dear to my heart because they are visible from the southern skies. Sometimes naked eye, you can see them if you are in the countryside. And those, because they are the brightest, have the best constraints on their motion around the Milky Way. They are around the Milky Way. And they are moving fast. And they again confirm the presence of that very heavy dark matter halo, but not within 20 kiloparsecs, not within the disk, but hundreds of kiloparsecs. There is mass out there. We have learned a lot about the Milky Way, but as I said, it's a very special place because we are within it, and a lot of the interpretation is biased by the fact that you are inside. So if you are inside a room and you're trying to guess how the building looks like, it's quite different. So that is when the rest of the universe becomes very useful. We have a picture here of our hero, the Hubble Space Telescope. It has guided our knowledge of galaxies for the last 20 years, and it continues to do so, way beyond what it was planned for its lifetime. This is a picture of the Hubble Deep Field. This is a very crazy story. In fact, one of our professors, Baram Mobasher, was involved in this project. There was some time that it needed to be decided how to invest. You have the Hubble Space Telescope, and the question is, what do you do with the time? And so there was a competition on ideas on what was the best usage of a very long number of orbits for Hubble. And the competition was won by this project that sounded crazy at the beginning. It was to point the Hubble to an empty space of the sky. Right? So the people, some of them were like, are you crazy? You have finally a telescope, you want to look at nothing. But some of the people were convinced that it would reveal something very important, and indeed it did. So this is an image of galaxies that go all the way, not to the Big Bang, but to what we knew then the earliest in the universe. So when Hubble stared at this portion of the sky that is as big as your thumbnail for 13, the equivalent of 13 days, this is what it saw. A universe full of galaxies. We didn't know this before. Nothing has peered so deep as Hubble did. What I'm going to show you is a flight through our local distribution of galaxies. It comes from the Sloan Digital Scale Survey, which is a different effort, also led by the US, and it shows us the immensity of it. Anything that you see is a real galaxy. It's not a simulation. This one is a real universe. You can see the diversity of galaxies. Some of them are red, some of them are fluor, which is indicating different ages of the stars. Look at the different shapes. You have round galaxies, these galaxies, you have irregular galaxies. Galaxies also distribute in this filament of something that looks like a web that we call the cosmic web. Galaxies also like to group. The same way that we have the local group, where only two of the large galaxies are together, there are bigger associations. You can see flying through here, for example, there, or there is a bigger one coming up. If you pay a bit of more attention, you will see that the galaxies that are in groups have a different color. They tend to be more orange than the rest that is in the field or isolated. All of that information is telling us, or is telling our models, how star formation really works and how to get the population, the stellar population of these galaxies correct. This video was created by Miguel, who used to be a postdoc here when I arrived. By the time, by now, he moved to his next job. But this is now again using your dark matter goggles how the universe should look like. An intricate network of filaments, completely dominated in mass by dark matter, and at the center of them, at the heart, there is a luminous component, like the tip of the iceberg, that allows us to actually trace that distribution in the universe. Modeling the physics of how stars form is difficult. Gravity, the dark matter simulations, they're kind of easy because it's only gravity, one law over and over and over. Once you want to now simulate how the universe looks like right now realistically, how the gas should look like and how the stars will look like, there are many more processes that come into play. You want to form a star, you want to cool the gas, you want to form metals, you want to distribute the metals, you want to put magnetic fields eventually. All of that is the core of what my group, many of them sitting in the audience, and Anson and Simeon's group are doing in our department. What I will show you is, I had the pleasure to join the illustrious team when I joined Harvard, and this is one of the movies that shows how the universe forms, but now in the visible light. So what you see here is not the distribution of dark matter anymore. This is dark matter, sorry. You will see in the future how the violence, how the gas, how the stars actually form in these computer simulations. At the beginning, you saw this already in the Milky Way movie. This is dark matter collapsing into dark matter halos. Those halos aggregate into each other, and they start outlining these fantastic filaments. Those filaments are a prediction of full dark matter. It's kind of cool that we get them. You will see now, this greenish light is starting to show the gas in the universe, and it shows the temperature of the gas. You see that at the center, there was an explosion here. We see at the center of this dark matter halo, there are huge explosions, energy depositions that are coming from supernovae exploding, but also from modeling the physics of black holes and their accretion of gas. With this kind of tool, we can now make realistic predictions of how the universe should look like in spectrum and also in visible light. We will see now the scale transitioning to a bit of pinky and white, slowly. That indicates where are the metals. The universe has started with no metals. It started only with hydrogen and helium. So those stars that you see exploding, they also pollute the universe with metals that then allow the formation of planets like Earth and eventually us. So our models can also trace the distribution of those metals and compare those predictions with observations from telescopes. So we move on. We started this journey with the Milky Way. How do we form really a Milky Way in cold dark matter? And I showed you the dark matter assembly for a galaxy like ours. That was gotten right, I would say, much earlier, 2005, we had a pretty solid understanding of what dark matter should be in the Milky Way. Only now we're able to form Milky Ways that in gas and stars look like the real Milky Way. And that is after a very deep search for the real physics of what determines or what shapes galaxies in the universe. So let me share this with you. This is an evolution of the Astro simulations. This is the posterior project is forming, again, is showing you the formation of a galaxy a bit more massive than the Milky Way, but similar. Again, filaments. Over here, you can see in a much more zoomed out the distribution of dark matter in the universe. And it is the dark matter, the one that provides the backbone of how the gas is now aggregating into the inner regions of this galaxy. You can see some pores over there. Those are those substructures, those satellites that our theory predicts. They also contain gas. Sorry, this is showing just the gas component. This is how the stars in the main galaxy look like at that time. And this one doesn't have time, but has redshift. So redshift has to get to 0 for it to be the present day. As a rotation, just to show you this filamentary structure and how the topology of the region looks like, very chaotic, that's showing you temperature in the gas. Velocities. You can see why theoretical models are just not enough. There is no spherical symmetry, there is no real things that you can follow with analytic calculations, and that's why numerical simulations become a key tool to understand the universe. By this time, redshift 1.2, which is about half the age of the universe in giga-years, the galaxy has already formed a stellar disk. If you think about it, it is pretty difficult to maintain this disk. Remember that there are a lot of satellites bombarding constantly the disk of the Milky Way, if all that matter is correct. So it took us a lot of effort to understand how to maintain this disk rotating, even though you're bombarding it with this dark matter subfields. What are we up to nowadays? So you hopefully have heard of the James Webb Space Telescope, was launched a couple of years ago, and is kind of the new toy or the new Hubble. This one is not located around Earth like Hubble, but it's in L2, which is farther away and closer to the moon. So there was a lot of stress on whether it would be able to unfold and actually become operational. Once that anxiety passed because everything was successful, it has revealed a lot of amazing things already in only like a year of full operation. This is a picture showing you the dust emission in, I think, 19 spiral galaxies in the nearby universe. It's astonishing. It's really, you can look at it for hours. It's just a fantastic description of how the gas and the star formation laws in the universe work. For us, simulators, this is a new benchmark that our models should be able to reproduce and explain. And there are a lot of our colleagues in the observational group in astronomy that is not so much looking at nearby galaxies, but also at the intermediate age galaxies in the universe. What JWST has also shown us as something intriguing. So this is the equivalent of the deep field for Hubble, but JWST can do it much faster, all right? Hours instead of days. So that is the technological advancement is amazing. But also because it's not focused on the same optical ranges than Hubble. You can observe things in the very early universe much better. The radiation of things in the early universe gets Doppler shifted until we get today, and JWST has been specially designed to capture that light. So what has discovered is a population of perhaps the first galaxies in the universe. And you have here in this blowout an example. So this is part of this, I don't know how to pronounce, JADES effort that is led by Brand Robertson in Santa Barbara, UC Santa Barbara. But many of our colleagues are participating too. And something that they have found is that these galaxies that are really just millions of years after the Big Bang is nothing in astronomical time. That is for us, just in the blink of an eye after the Big Bang. These galaxies are huge, very large, very massive. And this one is not the only one. There are many candidates that have been identified at redshift 12, 13, 14. What does it mean for lambda cold dark matter? It's a bit of a problem because, as you saw, our idea is that the universe starts very homogeneous and things grow, but it takes time to grow. So these objects seem a bit too massive to be consistent with the number of massive objects in lambda cold dark matter. So the community is very excited about JWST, and you see updates on this interpretation daily on the archive. A group that will say, oh, everything is consistent. Then the next group says, no, everything is inconsistent. Lambda serial is broken. So it's really exciting times to be working on that, especially these ones at the very early universe. Now, what is the future? I wanted to highlight some of our exciting advancements coming up. So on some of the areas over here, see if I can actually cancel this. This might actually work. All right, so direct detection of dark matter. New detectors. You see over here is one under construction, dark side 20K. Our colleague, Sean Westerday, I saw him earlier, and then I don't know if he's still there, but okay, Sean, hi Sean. Is part of this effort, is a multinational effort. This video is here just for you to have an idea of how these detectors look like. They're crazy. They are underground. You have to shield from radiation or cosmic rays or whatever that are on the surface. So they go in and build these gigantic tanks of, in this case, argon, trying to make that matter interact and capture that interaction and then claim a detection. So over here, we have Jared, who is graduating today. And I just wanted to mention, he was involved in some of the research leading to that, and makes us proud again. Jared is moving to a PhD in Santa Barbara. We wish him the most very best. There is a lot of exciting news also for gravitational waves. So you remember LIGO was detecting, or has detected, the first glimpses of these binary black holes interacting. The next thing to come is called Cosmic Explorer. John Richardson here in the audience is one of the experts and involved in leading the efforts for the detectors. We need, you can see over here, this is redshift. Again, big numbers is early in the history of the universe. Low numbers is here now, today. So LIGO, these are some of the detections of LIGO. They have been pretty much in the nearby universe. Has been amazing and worth the Nobel Prize. But the full potential of black holes as candidates for that matter is coming perhaps from much earlier in the universe. So these are the theoretical predictions for where the black hole binaries should be coming from stellar sources, but here are the primordial black holes. Very high redshifts and very low masses. Okay, so Cosmic Explorer is trying to reach that frontier to be able to actually test if that matter indeed is made partially or totally of primordial black holes. On the CMB front, a lot of efforts mentioning here, Simon Observatory and CCAT are both under construction in Chile, neighboring country to Argentina. And the idea is to improve on the accuracy of the measurements of Planck. Planck is already very amazing, but in order to constrain inflationary models that are explaining how we went from the Big Bang into something that is more similar to the beginning of the size of the universe, we need something called inflation. At the time of very rapid expansion, in order to understand more that phase, we need more accuracy. And this upcoming facilities, for which, Steve Choi, our faculty, newest faculty member, is also contributing to the development of detectors, are going to give us exactly those answers. We hope. On the side of my corner of the universe, Galaxies, we are extremely excited about two of the missions. There are many more, but I just had to pick two. Two of the US missions, the Nancy Grace Roman Space Telescope, funded by NASA. That's going to be like Hubble, but the field of view is going to be 100 times. So you can see over here this whole mosaic of, this happens to be M31. The field of view of Hubble is this. I don't know if you can see that small square there. So now this one with a much bigger field of view will allow us to survey the skies much more efficiently and to deeper magnitudes, revealing low surface brightness dwarf galaxies that we cannot see today. Even more exciting is the Vera Rubin Observatory, because that one is already ready to start giving observations. Roman is still under construction or under planning. Vera Rubin is almost already there and is expected to give us the first survey of the skies within a year. So Vera Rubin was designed also for the survey node, is able to rotate and map the entire sky in a few days. This is an amazing achievement, technological achievement. And again, the part that is closest to my heart is the study of the dwarf galaxies. They are so faint that we need of these new facilities to access them. And they will be our next probe of all dark matter. On the numerical side, we will continue developing our models and hopefully be able to improve our understanding of the universe. Thank you. Okay, we have time for a few questions, but while you think about the questions, let me just say thank you to the Cosmology Astrophysics particle group in the department for organizing these Frontiers in Cosmology lecture series, particularly Professor Jonathan Richardson was the person who put all this together in a relatively short time. So thank you, John. We'll take some questions. Maybe we can teach on the Oh, I see it. I see a question. Yes.
Why is there more spherical symmetry in the models?
Excellent question.
Sorry, what's the question?
Why there are no more spherical symmetry in models? Sphericity, as perfect as it is very unlikely. It requires of a perfect distribution that these things don't have. So the idea is that the universe is almost homogeneous, but it's not. And those inhomogeneities are giving you preferential directions for the accretion of the mass into the halo. And that imprints a shape, preferential shape for the structure. Now, measuring the structures or the shapes of these dark matter halos and filaments allows us to actually constrain the nature of dark matter. So the shapes of halos is used to actually discriminate different candidates for dark matter particles. So it is actually good that it's not spherical, but how non-spherical it is tells us whether, for example, it is full dark matter or dark matter can self-interact with itself, which would give you things that are more round, right? So shape is information, and it's good. Good question. What questions? I see a hand back there.
Yeah.
Oh, yeah.
So I'm not a physics major, but just very interested in the subject.
Why do we think that dark matter is a particle and not in wave form? Because, I've heard about the halo of the dark matter that envelops our galaxy 10 times further out than the size of the galaxy. Would we be seeing interaction in other galaxies getting close between dark matter halos or something, if there was interaction happening? So why are we not thinking of it that way?
Excellent question. We're not saying that there is no interaction, but any product of the interaction cannot emit in the electromagnetic spectrum, so we couldn't see it. So even if it was in a waveform that is interacting, we wouldn't see it, right? So it's useful to think about a particle. However, you can also think about modifying the laws of gravity, and that is actually pursued actively in the community. You can modify, for example, in the external side of the galaxy, you could say, in the low acceleration regime, Newton is not valid anymore, and it behaves differently, and that can indeed explain a lot of the universe. This rotation curve, the flat rotation curve, can be perfectly explained by something that just modifies gravity instead of assuming a new kind of particle. However, such models have not been as successful to give us a complete cosmological model that can explain from the Big Bang until today. And that's why we still cling to this idea of dark matter as a particle, because it gives us a framework that no other theory has given us yet. But if this could change in the future, someone works out the math of how the universe would behave with gravity. So it's a very valid question. Thank you.
Thank you.
All of these are people who are defined and difficult. Go ahead.
I'm not familiar with this information, so how does happen that the dark matter looks like filaments instead of
Yeah. Good. So what happens is, as I said before, if you want to get something round, it requires a level of symmetry that is very special. In most cases, you will always have one direction that will collapse earlier than the other. Okay? So what exactly has the shape of filaments and not sheets, for example, that is given by the nature of the dark matter particle. And in particular, its temperature. Cold dark matter refers to the velocity of the dark matter particle at very low. Cold means very low velocity. Those low velocities give you this granularity and gives you this filament. If you assume that dark matter had a much higher velocity at the early universe, it's what we call hot dark matter, that now completely rules out. And that one would collapse first onto sheets of dark matter and then break into smaller structures. Right? So that one is ruled out. But there is a candidate that is sort of intermediate called warm dark matter that is kind of high velocity but not so hot. And that one has very interesting kind of properties, because on larger scales you still get the filament, but on smaller scales it changes the structure of the halo on scales that might be interesting. So warm dark matter is still researched. It's not preferred, but it's still not ruled out. But it's basically given by gravity and how difficult it is really to get around things and the equilibrium that it requires in undergravity.
It's not exactly close our method, but it depends.
Okay.
10 years ago, when I was working on some stuff, we already speculated. I believe it was exactly 13.5 redshift, and maybe it was 18 black hole. And we already were like, okay, probably can be perimeter black hole because we got different amount of time. Now we're already have a full galaxy, so we need a black hole even earlier. So do people like, oh, right, like all black holes?
Yes. Do some people lose the sleep over it? How do you feeling somewhere? There is one of them trying to come up with dark matter particles that will actually help you do that. right? So if you assume cold dark matter, and you don't really know what the seeds of black holes are, it is extremely difficult, as I said, to fit these very large galaxies that have like very no time, much less to form a supermassive black hole. There are other models. Self-interacting dark matter has a property that would allow you to collapse very quickly in the inner region, forming a black hole of masses 10,000 solar masses already. That gives you a much better star than a stellar black hole. To start, accumulating and becoming an AGN in the universe. So that is a very unexplored in the sense of there is no right and wrong or clear theory. People are just throwing ideas and trying to make predictions. Very exciting field of work to understand what they will see on other missions.
Thank you.
Are you not going to want to come explain?
No.
All right, so, this is not my field, except that in my mind, I learned in a cosmology of my own, of course, as everyone does. So I'm wondering about these mug-sized particles that you said were in this room.
Yes.
And I would like to know how the heck do you know that?
Okay, so. Hydro told me.
That doesn't count. That is not acceptable.
The sentence is, there is about 1 dark matter particle in the volume of a coffee cup. We don't know the size of that matter particle. We don't know. You could imagine there is a particle with no size and it's in that volume. And the way it comes is quite, it's a very simple calculation. This is really not that difficult. It's just an approximation. So we know how fast the Milky Way is rotating, and we know how much stars and gas are here within a radius of the sun. So we know the amount of mass that is in baryons or stars and gas, and whatever is not there is dark matter. That gives us a density, the mass, and so now we assume a volume. And we can divide, and that gives an approximate density, and that's how the analogy becomes. It could be, wrong by a factor of 10. I'm sorry, it's fine.
So we're here and we're rotating around the sun, and everything that's going on is going on everywhere.
Absolutely, yeah. And there are, for example, dark matter theories that predict fluctuations on the distribution of dark matter as the sun rotates around. So there are experiments trying to plot this. They are, of course, periodic because the sun goes around always the same way. So it's very exciting to try to put constraints on that matter nature that way.
And are all of these things going in a counterclockwise direction? Or do they change, or some way or other?
The direction is given by the force of this large scale structure, right? So the gas comes already with some angular momentum. The exact orientation of that angular momentum depends on the neighborhood and the neighboring structure.
Okay, thank you.
Thank you. So we can go ahead. Yeah. Okay, let's take you around time.
I'm curious, how is the cosmic, the microwave background, what is that measurement take, like 300,000 years after Big Bang? Because for temperatures and all for stars, when you point at a star and try to extend the folder or something, how does this hold that map that you?
Well, an excellent question. Yes. I'll take the opportunity to tell you an anecdote of how it was discovered. So the cosmic microwave, the universe back then, 300,000 years, it's expected to have a few thousand degrees. However, because of Doppler effect, the universe is expanding, it shifts the emission of light. It's actually detected in microwave. So what happened, there was a telephone company that wanted to install a new antenna. There were these two poor engineers trying to, install it and make the measurements. And they, pointed somewhere and they found an emission, pointed somewhere else, emission. So they thought it was a problem of the antenna. Because it was everywhere, they thought it was on the surface of the antenna, and the most likely explanation was perhaps those poops, right? Because it was this pattern. So they went in, clean up everything. The emission wasn't still there. So it took a few years until cosmologists got heard about it. And they're like, oh my God, this is becoming microwave. So it's just emission, it's a signal that is shifted and it's at 2.7 kelvin per day. But the universe was 1,000 Kelvin. Okay, it does the shifting. But we expected a given shape in that distribution of energy called black body spectrum. So when we found that pointing the unit, that there are 10 at different parts in the sky, and you record the measurement of the function wavelength, and you see that black body emission peaking exactly at 2.7 Kelvin, that was maybe away.
So, there's a very distinguished, member in the audience that is a little impatient for this to end, so we'll have, there's one question here and one here maybe, and then we'll invite the special person in the audience to come and say hi to.
All right.
Mom.
Okay,
One, here, and then I think there was one.
okay, we'll start here.
So what happened first, dark matter or the Big Bang?
Nice.
Stalling.
The Big Bang. The Big Bang is the beginning of everything. It just somehow the universe started with the Big Bang and suddenly it was dark. That's kind of the start, the extent of my understanding of this part of the universe. So definitely the Big Bang is the beginning. All right. So in that moment, the energy of the universe is created. Okay. And after that is this inflationary period, and after that is the expansion of the universe given by that energy. Right. But the dark matter came after everything began. So chronologically, it has to be considered dark matter later. Is there a final question?
Ask, do we have any predictions for the properties of a dark matter particle? Like, for example, its spin, like would it have a fully super spin or would it even have spin?
We had a dream, we had a candidate. That was the dream. They were a bit better defined properties for that kind of galaxy, those kind of particles. I was sitting in, workshop 2010, and people was like, these simulations are all wrong because next year we're going to know exactly what that matter is. We're going to have to run everything again. We should not do it now. 15 years later, we're still here with non-infection. The week that was the best candidate because it's really promising to explain that has not been found yet, even though there's still some region of parameter space. So right now, it's going to be done. Whatever dark matter particle model gets, proven or disproven, but it's really not a hint of what it could be. I will probably disagree, but on the details, I'm sure that I will get more information. From our business point of view, it's more like, we don't know, it is dark matter, that is self-interact, is it body dark matter, all of those candidates are completely different in nature and are not.
This is wonderful. There's so many questions. So thank you very much. So this was our first in the series. So we'll hope to see you back many, many times. Make sure you're in some of our mailing lists. This will be regular thing. Thank you so much. May I introduce, can you come here? So we have a special audience. That's part of the reason we're